This is page 4 of the parametric equation notes, and this is using general parametric equations for motion. And we did this with the ships in the fog problem, but we're going to look at a more general sense because motion can also represent motion of something thrown into the air, for example, as well as motion traveling across the ground. So in general, the equations for motions are shown in this box here. The x position at a certain time t is represented by the initial position in the x direction plus the velocity in the x direction times time. Velocity is just the slope or the rate of change of the equation. So that was the slope in the linear equations we did for the Helsinki and the Andy Doria problem. Y of t is the initial y position plus velocity in the y direction plus times time, or this is the slope. Now, there is an additional term that we add if we're throwing something into the air and gravity is involved. So we didn't have this term when we talked about the two ships because one wasn't being thrown into the air. They were just traveling along the ground. So this is omitted if gravity is not involved, if this is not projectile motion. Gravity is negative 9.8, and this should say meters per second squared, or 32 feet per second squared. And so this turns out to be, if you do 1/2 plus 1/2 times negative 9.8, you end up with negative 4.9. And so it's going to be negative 4.9 t squared that we will add at the end if we are using projectile motion, throwing something into the air. So this is just showing the equations written as x sub t is x sub 0, the initial position, times vxt, velocity in the x direction, times time, velocity in the y direction, times time, and so forth. In physics, it was you looked at displacement in the x direction equals initial displacement in the x direction times initial velocity in the x direction. When you put sub 0, it just means initial. So that's what these variables are telling you. There's Mrs. Slagle announcing the cast and crew. Supper's ready. Good to know, Mrs. Slagle. Thank you. Okay. Time is equal to t, and initial x and y position is when time is 0. So when we do the sub 0, that's why it's initial time. Velocity is in units of distance divided by unit of time. And since velocity is a vector quantity, x and y velocities can be negative, as we saw in the Helsinki. So if we look at what the equations we got for the Helsinki in the previous problem, notice that here, the 900, that's the initial x position. And negative 3, which is the slope of this linear equation, is the initial velocity, initial x velocity, or initial velocity in the x direction. For the initial y position was 0, so initial y is equal to 0, and the y velocity is 2. It was 2 millimeters per minute. Okay. Initial x was negative 3 millimeters per minute. So we used these same equations in the previous problem. You just didn't realize that's what you were using. So let's look at one where we have something thrown into the air now. We have a ball. It's going to be thrown from an initial height of 2 meters with an initial velocity, and this is supposed to be 30 meters per second. Somehow the 3 and the 0 got separated here. 30 meters per second at an angle of 25 from the horizontal. So actually I'm going to draw this a little farther over to the side because I'm going to need 2 pictures in here. So basically we have something that it goes up and comes down like that, and it starts at 2 meters. The initial velocity, actually I made that a little bit too steep. Let me make that less steep. It kind of is a little bit shallower like that, because the initial velocity is at an angle of 25 degrees from the horizontal. So this is 25 degrees right in here, the initial velocity. So basically we're saying that's, if we just drew a vector representing that initial velocity at an angle from that initial starting point, it would be at an angle of 25. So let's draw something just to represent the velocity. So if this is my horizontal direction and my vertical direction, my initial velocity is 25 and my initial is at an angle of 25 degrees and it's 30 meters per second. So we can think of this as a vector at an angle of 25 and has a magnitude of 30. And we have two other vectors, a vector in the x direction, which is the velocity, initial velocity in the x direction, and a vector in the y direction, which is the initial velocity in the y direction. And we know that, for example, sine of 25 degrees is Vy over 30. Therefore, Vy is 30 times sine of 25. I'm just going to write that up here. So, for example, sine of 25 is equal to velocity in the y direction divided by 30. So 30 sine of 25 is Vy, and 30 cosine of 25 is Vx. So I'm going to write that down here. Velocity in the x direction, initial velocity in the x direction is 30 cosine of 25 degrees, and initial velocity in the y direction is 30 sine of 25 degrees. So we know that, and that's actually the slope. We could put that into decimal form, or if we want to, or we can leave it. This would give the exact values. I'm going to change this to what your sheet says. X of t then is the initial x position. Well, the initial x position is 0. So basically 0 plus 30 cosine of 25. That would represent the slope. That number, if I do the decimal equivalent of 30 cosine 25, that's the slope of this little xt equation. That's the rate of change. Actually, slope's probably a bad way to describe it in this case just because we have a pair of equations. But if I was just looking at the x direction, that tells me how much the x direction, x component is changing for every second in this case. Y of t then has an initial position of 2 plus 30 sine of 25, which is its rate of change, times t minus 4.9 t squared to represent acceleration due to gravity. So it's being pulled downward with the force of gravity. Now I can graph these two on my calculator and see what they look like. So if I go to my calculator, I already have the parametric equations, and I already have them typed in because to save a little time. The only thing I need to tell you is when we're in radian mode, which we still are, if I go up here, see I'm in radian mode, I can go ahead and use degrees as long as I type in the degree symbol. So if you go to the pi button, you'll see that underneath pi is the degree symbol. So I'm going to escape out of there. I've added that in. Also notice that you close the parentheses before typing t because I'm not taking cosine of t. I'm multiplying t by 30 cosine of 25, and I'm multiplying t by 30 sine of 25 degrees here. Now if I go ahead and graph this, so I'll go ahead and push enter, you can see that it shows the ball going up but not coming down. I need to add some values to my x max and my y max, x max and y max, to see the entire path of the ball. So I'm going to go to menu to my window settings, and I don't really need any negative values for x or y because time and both distances are going to be positive. X max, it turns out I think that about, I don't know, 100 is good for that. I'm pretty sure. I don't know. I'll just do 10 for my x scale. Y 0 to, trying to think about how high it goes. Let me say 25. I'm putting these, you're wondering where did I get these values from? Well, I know basically what the graph looks like from having done it before, but you would have to do a little trial and error to figure those out. So there's my graph. Actually, it turns out my y max is far higher than I really need. So I can make an adjustment by clicking on it and just adjusting it here. So I think I'll just make it 12. There, that looks a little better. So if I wanted to trace this graph, I'm going to move the label out of the way because if I trace this, actually I may even hide it. Do you know if you do control click, you can hide something? That's very nice. I'm going to hide it right now so I can see the tracing better. Now if I go to trace this graph, right there, graph trace, you can see what is showing down at below is it shows me the time, 1.5 seconds, and the, yeah, when I move my cursor, that doesn't help, and the x and y coordinates of the ball at that time. So it's telling me, so if I trace up here, let me actually type in 0. When I type in 0, that gives, I can type in anything I want to for t. That tells me that at time 0, notice that I have x is 0, y is 2, which is my initial position. Then if I scroll along here, notice, for example, at 0.7, oh, let's go to 1 second. At 1 second, I've moved 27 meters in the x direction, and I'm 9.7 meters high above the ground. Okay, so I can trace this and get some answers to various questions, and you'll see the rest of below this now there's some answers to questions. And I'm going to actually go to a different page that I created that has a lot of graphs on it so that I can answer some questions about how do you do this. Okay, so here's my equations, here's my graph. I typed in 0 for t to get the initial position. This tells you the x position, the y, and the time. So when does the ball hit the ground? Well, the ball hits the ground when y is 0. And if you just trace it, you can see it goes up and down, and here's when it hits the ground. Now, when I traced it, I got 2.7 was before it hits the ground, and when I got 2.8, it was after, like past, underneath the y-axis. So I just kind of played around with making it 2.72, 2.73, 2.75, different things, and tried to find sort of approximately when y was 0. So this is just an estimate that when it's at about 2.73 seconds that it takes for the ball to go up and then come down and hit the ground. And that happens about, now x is about 74 meters from where it was thrown. So that actually answers the first two questions. On the graph, so this is approximately, when does the ball hit the ground? At 2.73 seconds. And how far does it travel horizontally? Is approximately 74.2 meters. Now, if I want to find out exactly when it hits the ground, what I need to do is solve an equation. So if I know that when it hits the ground, y is going to equal 0. So I'm going to use my y equation. So I'm going to scroll back up. Notice here are my two equations right here. I'm going to put it in 0 in for y and solve for t. Now you do see that we have an issue here that is going to be a quadratic equation. 2 plus 30 sine of 25 degrees t minus 4.9 t squared. Now if I write this in the order of a quadratic equation, it's negative 4.9 t squared plus 30 sine 25 t plus 2. So if I plug in, that means a is equal to negative, that's 4.9, not 49. If I can get the, for some reason the decimal point is not showing. There we go. Negative 4.9. B is equal to 30 sine of 25. And C is equal to 2. So you need to use the quadratic equation to figure this out. We'd plug in, so if I go through, and I'm going to go ahead and pause the video and do that, and you can do that too and make sure we get the same answer. Okay, just to remind you how to do that, I did negative 4.9, stored it to A. You do Control var to store it, and I stored a number for B, I stored a number for C, I typed in the quadratic formula, I got two answers, a negative one and a positive one. So if we go back and look, and there's the 2.7366, so it looks like 2.737 seconds approximately is when it hits the ground. But what's this negative number? If we go back and look at our graph, the negative number is when, before I threw the ball, basically, it would be another place where it's on the, it would be at 0 for y, but it would not make sense in the context of the problem. So I get here that t is equal to negative, I need to go back and look and see what those two numbers were, negative 1.49, 2.7366, negative, oh gosh, I forgot already what it was. 0.149. 0.1, that's what, sad when you're old, negative 0.149 and 2.7366. So this is not the one I want, but this would be the correct answer. Now, could you get a pretty good approximation by tracing? Yes. Do I want you to know how to do it algebraically? Yes. So make sure that you can do this both ways. Okay, how far does it travel horizontally before it hits the ground? Well, this is much easier than the first one because all you have to do is say, well, I know what time it hit the ground. To find the horizontal distance, I just put the time into the x equation. So you just say x is equal to 30 cosine 25 degrees times 2.7366. So I just take the number of seconds here, plug it into the x equation. So if I go back to the calculator and do that on my calculator page, then I can just pick up this value here. I don't know if I can, I'm not actually sure if I can copy that exactly, but maybe I can go up and grab this answer times, we'll see what this will give me. Two different answers. Obviously I won't want the negative one. 30 cosine of 25 degrees. So push enter. It gives me two different answers, and my second one there is the 74.406. Okay, so 74.406 meters. Okay, so pretty easy to do the second part. Now, how high does it go? Okay, how high is a maximum value? This is one where we don't have a direct algebraic way to do a maximum value just because we haven't learned the derivative yet. That's how you would do it. So this is one where I would allow you to trace. However, there is another way to think about it too. We know that it's going to be at its maximum value halfway between these two times. So if you take the average of these two times, that's going to be when it's at its maximum value, because it's going to be halfway in between the two x-intercepts. And then you could plug that in to find how high it goes. That would be one way to do it. This would be one, though, where it would be okay to trace. That would be fine. I'm not sure if I can use the maximum feature in here. Let's check it out if we can use the maximum feature while we are on this thing. So I'm going to escape out of trace here, and I'm going to go to menu, analyze graph, and maximum. And let's see if it's telling me, it's asking me graph. Let's see what's this. Click the function graph and then click the left and right search bounds. Okay, apparently this is not allowing me to do this unless it's in function mode. So that particular feature doesn't work in parametric mode. So at this point you can just trace to find that. That would be fine. But let's do remember that it's going to reach its maximum height. X, or time, is going to be the average of these two times we found, negative 1.49 plus the 2.7366 divided by 2. So if we find that, that should give us our time. So I am going to go back to the calculator and go back to my calculator page that I was just on. Okay, so if we take negative, okay, and notice that this comes up as answer negate. I want to negate this, not subtract. So negative 0.149149. I'll give a couple decimal places since I have it. Plus 2.736608 divided by 2. Okay, so 1.2937 seconds. And then we can plug that into the y equation to find height. So I'm going to go ahead and do that while I'm at it. So if I plug that in, this is going to be, why don't I just say, what is my equation? 2 plus, actually let me do this, let me pause and type this in. It's easier for me to type with 2. Okay, you can see what I typed in down here. I just substituted my time for t and for t squared, and if I put enter, push enter now, doesn't want to push enter for some reason. There we go. There's my height. So 1.29372, there's 1.29 seconds. I'll be at a height of 10.2, and that's pretty close to what we traced. Okay, so back up here. So this was 1.29 seconds. So then we would say y of 1.29 is equal to, and we have 2 plus 30 sine of 25 degrees times 1.29 minus 4.9 times 1.29 squared. And that got us 10.2 meters. So you can see that verifies what we got when we traced here. So you can see at about 1.3 seconds, we're about at 10.2. Now the last question is, will it clear a wall that is 60 feet away from the point where the ball was thrown? So what I did was, basically we're saying we have a wall that's 5 feet high at 60 feet away. So this would be about 60 feet away. The wall's about 5 feet high. This is at 60. I don't really know exactly where that is. But notice I've traced past 60. I've actually traced to where my y value is, or my x value is 62. So I've actually traced past the fence, and I'm still over 5 meters high. So it does obviously clear the wall. I'm not exactly sure where the fence is. Maybe the fence is more like here. Not exactly sure, but I have cleared the wall. So obviously the answer is yes, but how could we figure that out for sure? We're using the equations. Well, I know that when y is 5, or when x is 60, I want to know if y is bigger or smaller than 5. So I use my first equation, so equation number 1, and I put in 60 for x. So 60 equals 30 cosine 25 times t, and I solve it for t. So 60 divided by 30 cosine of 25 is equal to t. And let me see what that is. So 30 cosine 25. Let's see. Oh, hang on. Once again, let me pause and come back. Oh, wow, I just remembered something cool about your calculator that I should tell you. If you go back and look at the equations that I used for this particular graph, my equations happen to be x3 of t, y3 of t. Yours may be different. Yours may be x2 or y2 or whatever. But go back and look and see which equations you are. All I have to do on my calculator page is to type in x3 of and put a number in for t, and it will automatically calculate it, or y3. So that'll save me a bunch of typing. So let me just show you that on the calculator page. First of all, I did do 60 divided by 30 cosine of 25 degrees. And now that tells me the time at which the ball is 60 feet away from where it's thrown. Now I want to know how high it is at that time, so I can see if it clears a 5-foot wall. So I just want to know the y coordinates. So I could type in 2 plus 30 sine 25 times 2.206 plus minus 4.9 times 2.206 squared. I can type it in like I did just previously with the 1.29 right up here. Or I can do this so much more easily. I can say y3, and then in parentheses, I can go up and grab this number, put it in, and push enter, and there is my value. So this tells me when I am at 60 feet horizontally from the point at which the ball was thrown, the ball is 6.1 meters in the air still, and this occurs at 2.2 seconds after it's thrown. So that's pretty great information. That y3 is a nice little tip. So whenever you're plugging a number into an equation, you can always do that, whether it's an F1 or a Y3 or an R1. That works for polar 2. It works for anything. So we'll go back and answer this question. This was 2. Oh gosh, I forgot the number already. This was 2.206. So t equals 2.206, and then if we do y of 2.206, we ended up with, what did we end up with? 6.1165, so about 6.12 meters. So basically we're saying here that we clear the fence by over a meter with no problem. So this is the way you answer questions with a combination of looking at the graph and algebra. I want you to be able to do both. So make sure that you, when you do your homework, you do the answers using algebra, using the equations, as well as using the graphs. So happy problem solving. Don't you just love it?